Okay, can we continue?
Can Doctor.
Okay, so welcome again. So this is chapter 2, architecture of the ARM processor. So in this chapter, we will learn in detail, more detail as compared to the previous one, the architecture, what is inside the ARM processor, and how it works. So what we will learn in this chapter is this. We will look at the core architecture, the inside, the circuit, the block diagram, how the things is connected to get to each other. And next we will learn what we call a programmer's model. This is the model that is used by a programmer, and for us as a programmer, we will program the microprocessor later on. So as a programmer, so we need this model to be used in writing the program. And we will look at memory organization. So this is very important in every microprocessor actually, how this microprocessor organize the memory. And the last part will be the instruction set architecture. So you have been introduced to instruction set architecture before. So in here we will learn uh, in more detail and specific to processor. Okay, so we go to the first, which is the core processor core architecture, and this is the ARM architecture block diagram, the simplified block diagram. Of course, the real one is more complicated. You will have many more wire, many more signal, many more component. But this is the simplified version of the the block diagram. So this is very similar to what we have learned in in data design, where we have learned how to design a very simple processor, and this is the more complicated one, where we have the ALU here, right? We have data in register, where the data come in, right, to the data in register. We have the instruction decoder here that will generate the control signal. So the instruction will come from the memory. So here is inside the core, the inside of the microcontroller, microprocessor, not including the memory. All right, so the memory will have another blocks, the memory part. So this is what inside the microprocessor core. So the instruction will come here in the data register and go to the instruction decoder to decode the instruction and generate the control signal. All right, the data also come from the memory through this data in register. All right, and not go to the instruction decoder, but will go to the B bus here. All right, so this B bus will go to the ALU through the barrel shifter here. So this is basically the shifter that you design in the design. So it's just a shifter. So whether you want to shift the data or not, here, right? So you can pass the data from here through the ALU, and you can from the NU you can go to the register bank. So in the register bank, there will be many register, general purpose register that we can use for general purpose data processing, right? So we will have later on, we will see we have R0, R1 until R15 that we in the register bank. And we have A bus here, all right, to feed to the ALU also from the register bank, and also go to B bus from the bank. For example, we want to add number, right, from R0 and R1 here, so we can put value from R0 in A bus and put value from R1 in B bus, and we can add and we can put back in R0 or R1 or R2 or any register that we want, right? So that is how it works. And also we have the PC. We just learned in a previous chapter just now. Well, the function of PC is to point to the next address of the instruction to be executed, right? So this is the PC, and this is the one incrementer. This is the bus, right? So increment here, and this is the address register where it will generate the address that is necessary to access the memory location. So we will see later what is the size of the memory for this uh, processor, right? And in this case, the address bus, the size is 32 bit, from bit number 31 to bit number 0, 32 bit, and for data is 32 bit also, 31 to 0, right? And this is data out. Data out means that from the processor we want to send the data into to the memory, so through this register, right? So that is basically the block diagram, general block diagram of the uh, ARM processor core. So let's look at this. This is the explanation where I have explained just now. So let's see what it says. ARM core contain functional unit, the data path component. Yes, this is the data path, right? Connected by data, address, and control buses. So you have data bus here. All are data bus. This is data bus. This is control bus, and this is the address bus. The arrow represent the flow of data, the flow of data. The liners represent the buses, and the boxes represent either operation unit or storage area. So this is operation unit. ALU is operation unit. This is operation also, decoder. Storage is the register bank, is the storage. Register, data in register, data out register is the storage. Address register is the storage also, right? The data enter the processor core through the data bus, and data may be an instruction to be execute or data item. Yes, just like I said before, here enter here can be instruction or data. So in microprocessor we have two types of data actually. One is the instruction itself, the instruction that instruct the microprocessor what to do, and also the data that we want to process, right? So can be data or instruction. So we'll go through this data register. If the instruction, it will go through this bus to the instruction decoder. If the data, it will go through this bus to the ALU or to the register bank. ARM implemented using von Neumann architecture. Data, item, and instructions share the same bus. In contrast, ARM implemented on Harvard architecture implementation use two different buses. So this is a knowledge for you. There are two type of architecture in processor architecture in that we have in nowadays. The first one we call it von Neumann, and the second one we call Harvard. So some of the microprocessor implement von Neumann, and some of the microprocessor implement Harvard architecture. But ARM, we have two, because ARM is very big and we have many versions of ARM architecture. So some of the ARM architecture implement von Neumann, and some of the ARM architecture implement Harvard. What are the different? This is the different. So this is von Neumann architecture implemented in our modern laptop, PC, right? Normally using von Neumann architecture. And von Neumann architecture is something like this, where program and data memory share the same bus. Means that if you want to get the instruction from the memory, you will use this bus. And again, when you want to get the data from the memory, you will use this bus. All right, means that you use the same bus. But in Howard architecture, you will see that data memory and data memory and program memory is using different bits, different bus. When you want to get the data from the memory, you use this bus. When you want to get program or code or instruction from memory, you use this bus. All right. So you have separate bus for program and data. What is the good for this? And the good is that it is faster, because at one time you can get the data and also get the code from the memory at the same time, simultaneously. All right, so this definitely faster as compared to this one, because this one you need to get the instruction first before you get the data from the memory. All right, one by one. So in terms of efficiency, all right, performance, of course this one is better, the Howard architecture, right? Because you can do two job at the same time. All right, but in terms of cost, of course this one is costly because you need more wire, right? And of course different circuitry, right? More complicated. So in terms of cost, this one is definitely more cost as compared to this one. So the one that we will use in our course, we will use microcontroller Cortex M3, yeah, and this one will use the Howard architecture, which is this one, right? So in our course, we will use Howard architecture because the device that we use is ARM Cortex M3, right? This is from M profile, and then it's used the Howard architecture, yeah. The instruction decoder translate instruction, so we know this already, so it should be no big deal, right? So we have this. And next, the ARM processor, like all the RISC processor, use the load store architecture. So you have been introduced to load store architecture last week, in the previous lecture already. What is load store architecture? And this is implemented in most of, or I can say all the RISC processor, because it make the microprocessor less complex, and of course, just like we learned before this, RISC takes more steps in order to do or to execute the task. So load store architecture means that you have extra steps in order to do something, all right, or to perform any task. For example, when you want to add number from memory, right, in the CISC computer, you have the instruction that can directly manipulate add the number in the from the memory. Means that one instruction, you can actually do something like this. Again, we have the instruction to do something like this. For example, in R0, we want to add the number from memory location 20 plus memory location 21 and save the result in R0. We have the instruction to do this, right? The detailed instruction is not like this. We will learn the instruction in chapter 3, but this is what we know so far, right? Using the RTL notation that we have learned in the design. So this is the notation that we use to add data from the memory. This is memory. M is a memory name, and in a square bracket means that the location of the memory is location 20 or address 20. Add with another data from the memory location 21, and we save the value in R0. This is what we can get from CISC. But in RISC, what you need to do is to first to transfer, which is load, yeah, the value, the data from memory to R0 first, and then another one to R1, for example, and then number 3, you add. Okay, you need 3 steps. You see, RISC. So in CIC, 1 step done, right? You can add directly from the memory to R0, get the result. But in RISC, you need to load. This is load. You need to load the data into the CPU, the register R0, and the next one into R1, and you add from the register and you get the result, right? You need 3 steps here compared to CISC, only 1 step. So that is basically what is meant by load store instruction. Load store architecture. Same thing when you want to, for example, and store, CISC may have the instruction that you can directly store to the memory. Okay, we store the result in M23, but in RISC you need to store, all right, from so this we call store. Okay, so this is basically what is load store architecture. Okay, let's see what it says. This means it has 2 instruction type of transferring data in and out of the processor. Load instruction, yes, what we saw just now. Load instruction copy data from memory to register in the core, and conversely, the store instruction copy data from register to memory. Yes, this is load and store. There are no data processing instruction that directly manipulate data in memory, just like this. This one, huh? This one is manipulating data directly in memory. There is no instruction, such instruction in RISC. RISC, we need to do this. Thus, data processing is carried out solely in register. Data items are placed in the register file, a storage bank made up of 32-bit register. So in ARM microprocessor, the size of the register is 32-bit, right? The one that we use in nowadays ARM microprocessor, especially A profile, we have up to 64-bit register already, right? But the one that we use, Cortex M, is 32-bit register. Since the ARM core is 32-bit processor, most instructions treat the register as holding signed or unsigned 32-bit value. So the register that we will use later on can be used to hold signed number or unsigned number. That's why we learn to convert to the 2's complement just now, because it will treat we will treat the number either in signed or unsigned 32-bit value, right? But of course, although it is 32-bit value, or what we call the word, yeah, it is also can be used to manipulate 16-bit value also, which is half word, and also byte value, which is 8-bit, right? Should be no problem. ARM instruction typically have two source register, right? We have two source registers. We call it Rn and Rm, but you can use one only also can, yeah, and a single result or destination register called RD. Source operand are read from the register file using internal buses A and B respectively. So we know already that we have buses A and B that is for we call it for operand, yeah, source operand. So again, come to this, for example, R0 R is equal to R0 plus R1. So this we call the operand, right? Source operand. And this we call the destination operand. Anything that need to look at here? I think the same thing that I have discussed. So you can go back and try to read this. Next, we will go to the what we call the programmer's model. All right, this thing, the programmer model, the second part of this chapter. So a programmer model shows what the CPU has available to programmer for the execution of program or sequence of code. It covers the CPU resources for execution of the CPU's instruction set. Right. So programmer model is a model that shows or provide the programmer with the available resources that can be used in writing the program. The model does not show detail of hardware. This is very important. This model does not show the detail of hardware. It means that this is not programmer model. All right. This is detail of hardware, right? What connect to what. This is in terms of hardware. But programmer model would not cover function that cannot be observed by CPU instruction. So this is programmer model. So this is the resources that we as a programmer need in order to write the program later on. What we have, how many register that we have? So we have in the register bank, will have 16 32-bit register from R0 until R15. And we also have what we call the spatial register, 5 spatial register here. Comprises of what we call the program status register. We will see later on what is a status register. Interrupt mask register, where we will cover this. We will learn interrupt in chapter 5. And the control register. And when we look at this, we will see that we have here the from R0 to R12, 13 register. Here are what we call the general purpose register. Means that we can use for general data processing. All right, from R0 to R12, and from R0 to R7 we call it low register, and from R8 to R12 we call high register, and all the size is 32-bit. And R13 is stack pointer, and stack pointer comprises of 2 stack pointer. What is stack? We will learn stack in detail in next chapter. Maybe I will explain in detail in next chapter. Yeah. So R13 is used for stack pointer, because stack we will if I can introduce you a little bit to the stack here. So stack means that a location in the memory, somewhere in the memory that we can define. So it is actually a part of memory that we can define, right? And the location is in the memory is like this. And remember, in the memory, the size for one location is 8 bit. Yeah, in the register, in the CPU, the size is 32 bit. So the stack, normally we use the stack is for when we want to save a data, in the form of first in last out implementation. For example, we put the data in all right, so this we call the bottom of stack. This is the bottom of stack. So we put the data, for example, 1 2, all right, hexadecimal, and then the next data will be 3 4, the next data will be 5 6, and so on and so forth. So this will be what we call the top of stack. And if we want to receive the data later on from the stack, we need to take the data from the top. Yeah, we cannot take the data from the bottom of the stack, right? So 60 6 5 6 will go out first, followed by 3 4, and the last one will be 1 2. So this is how we implement the stack in microprocessor. All right, first in, last out. First in, last out. Okay, so this is the stack pointer. So it will use to store the address of the stack. All right, so here of course we have the address. Okay, so it will store the address of the stack in the stack pointer, right? That's why we call it pointer. And we have two. First one we call it main stack pointer. This is used in for the main program. Yeah, and the second one is we call it. This one is for example, for using in OS and so on. I mean that used by system. Process stack pointer is for user program. When we write the program and we want to use stack, we will use the process stack pointer, right? Art14 is called link register. Link register is used for to store the return address when we execute the sub program or subroutine. Later on, we will see in the next chapter also, we will learn in detail. So maybe I can also explain a little bit here what is return address. So again, when we write a program for a microprocessor, we will store a program in a memory. And again, a memory is drawn uh, like a building, right, with many levels, right? Again, this will be our memory, and we have many locations to store the program and also data. And for example, this is for data in this case, and we have many more. And let's say, for example, This is location number 0, this is number 1, number 2, number 3, 4, 5, 6, until this one is maybe location 20, 21, 22, and so on and so forth, right? And inside here is the program. And again, the program is stored in the form of binary number. And let's say, again, this is 8-bit. So the program is just a data, for example, 8-bit data like this. And we have, all right. So again, in our microprocessor, we have what we call a PC, right? Just now to point to the next instruction to be executed. And now we have another one here. We call it link register. LR, link register, and this one is PC. Okay, so in writing a program, so sometimes we have a function to be called, right? Just like in your C programming, right? You call function A at some point of your program. So same as this here in the microprocessor. So for example, whenever our program execute this instruction, so of course the PC will point to the next instruction to be executed, which is number 3, right? Number 3. So, and the next instruction, for example, this instruction force the microprocessor to jump to the location, to the new location, not in sequence already, not go to number 4. All right, means that you branch your program, you call a function, and your function is here, for example, function maybe function delete, or any function that you want in your program. All right, so the microprocessor need to keep what we call the return address after it finished this task, right? So this is a function task. So in order to go back from here to here, because the PC now, when you execute this instruction, the PC is not number 4. All right, it's supposed to be number 4, but because this instruction force your microprocessor to jump to this location, which is 20. All right, so PC will change to 20, but after you finish this, you need to go back to the next instruction after you jump here, which is number 4. So this number 4 will be stored in link register. All right, the return address after you go to this subroutine. All right, so the process is something like this again. So let's say, for example, this instruction is to force your microprocessor to jump to this location. So in normal execution, for example, your microprocessor is executing this instruction at location number 2, and of course in the PC will be number 3. Next, when it's finished, it will go to the next instruction, which is instruction number 3, and put 4 in PC. All right, because the next one should be number 4 to be executed. All right, and go to number 4. Yes, it will go to number 4, and it will put number 5 because number 5 is the next to be executed. Right, but instruction number 4 force the microprocessor to jump to the new location, which is 20. So the microprocessor need to put 20 in PC, but 5 is the return address. Because after this, it will need to go back to 5. So 5 will need to be stored or saved in LR, and PC is updated to the new location, which is 20, so that your microprocessor can go to 20 and execute this, and after that it will return to number 5, where PC is loaded with 5 again from LR. All right, so that is the function of LR or link register, and we will see in detail in the next chapter. All right, Art 14, and the last one is actually the PC. Art 15 is PC, and we learned already what is PC, and of course we will see in detail in the next chapter. All right. Next is the spatial register. So the spatial register is basically not used by the programmer. I mean, programmer not often write or put the data in the spatial register. Normally, we will read the data from the spatial register. For example, the status register, it will give us the status of the processor after executing some instruction. For example, the arithmetic instruction. For example, when we add a number, if we have overflow, so we will check whether the operation give us overflow or not here, or we produce the zero, or the result is negative or positive. We can check here in the program status register. All right, so in the previous course, the digital design, we also learn what is the status of the our circuit. For example, we design the ALU, right? So we have extra status signal to tell us whether the result is zero or not, overflow or not. That is the same as here. And the next is this group. This is mainly for interrupt mask register. What is interrupt mask and what is interrupt? We will learn in detail in chapter 5. Yeah. Interrupt is basically the just is like the name suggests. The interrupt means that we interrupt the microprocessor at some point of the program or data processing, or the microprocessor running the program. So at that some point we interrupt the microprocessor to do something else. So for example, the microprocessor run here this instruction, run this instruction at some time here, at one time here. For example, running when the microprocessor running this instruction at location number 4, we interrupt the microprocessor to do something else or to request for attention. For example, in your laptop, right, when you press the keyboard key, that means actually you interrupt the microprocessor. So for example, you run the Word, Microsoft Word software, all right? You do nothing means that the microprocessor will keep displaying the Microsoft Word interface, where you have the space for typing, right? But there is nothing happen. But once you press the key, all right, means that you interrupt the microprocessor to check what key is pressed and what to do after you press. For example, you press A, the microprocessor need to check, because you have many key. The microprocessor need to know what key you check. So there will be a small part of the program to check what key that you press, and if you press A, what the microprocessor need to do to display A in your Microsoft Word, for example, right? So that is interrupt means. What interrupt means, and interrupt can be many things. in this ARM microprocessor, there are two types of interrupt. We call it interrupt and exception. Exception is the interrupt that come from CPU itself. For example, you have issues with running the program, so the CPU, the microprocessor, will run the exception. For example, when you divide with 0 or something happen to your program, crash, blue screen, so that will be a exception. So interrupt is normally for external interrupt. For example, you move your mouse, you press the keyboard, uh, or you give any input to the microprocessor, that will be the interrupt. So what is interrupt mask? Interrupt mask is the way you want to enable and disable the interrupt actually. Right? There is a way, so there will be the interrupt in your microprocessor. So your microprocessor is able to respond to many type of interrupt. So as a programmer, as a designer, we have a way to what we call mask the interrupt or disable or enable the interrupt. We use it, we call it the interrupt mask. And the last one is the control register. So this control register is basically used to control the operation mode of your microprocessor later on. All right, we will see later what is the mode or the microprocessor mode, running mode. Right. So this is basically what is called by programmer model, and we will use this a lot when we write the program later on. Okay, so I explained this already, so you can go back and try to read this. Spatial register, so we have detail already. This is operation mode. So in ARM microprocessor, we have two operation modes. So the first one we call it handler mode, and the second one we call thread mode. All right, handler mode is basically the mode for the microprocessor to process the interrupt and exception. All right, and thread mode is actually for running the program. All right, and you also have level. We call it privilege and user level. Privilege means that a user or programmer, a user cannot access the part of memory, and user means that the user can access the memory, right? And this is how the Cortex M3 operation, when we start, this is very familiar, right? This is just like the state diagram. So when we start the microprocessor or we press the reset, it will go to the privilege thread first, and privilege thread means that this is running in handler modes. Before it will go to the user program or user thread, right? So privilege thread is normally the setting or startup code in your microprocessor, or in other case is the OS maybe, right? So you can change to user thread by using the control register, right? In the user thread, when the interrupt come, you need to go to the privilege handler again, right? Go to the exception handling here. So we'll change to the privilege mode again. All right, and after you exit from interrupt handling, you go back and so on and so forth. So this is done automatically by the microprocessor. No need to worry about this, right? So what we need to do is to know how it works. So our job is to write a program, and this thing will be executed automatically, right? And let's go into a little bit detail of the status register, where here the status register here, right? Where it is a 32-bit register also from bit number 31 to bit number 0 here. And when we look at the detail here, we can see that we have the flag, what we call the condition flag. This is exactly the same with what we have learned in the design. This n is negative to tell the microprocessor that the result of any arithmetic operation that you have performed give you negative or positive result. Bit number 30 is Z, give you zero result or not zero result. For example, if Z equal to 1 means that the result is 0. If Z equal to not equal to 1 or equal to 0 means that the result is not 0. All right. For n, if n equal to 1 means that the result is negative. If n equal to 0 means the result is positive. And C is carry, means that when we do arithmetic operation, if there is a carry produced, so n is equal, C is equal to 1. V is overflow, means that if we do arithmetic operation and the result is not feed in the register, for example, our operation is in byte and our result is more than 1 byte, so overflow occur and it's set to 1. Q is new for you. This is a saturation bit. We call it saturation bit. This is particularly in ARM processor. Other processor for most of the processor don't have this Q bit, but ARM have this saturation bit, and it has one special instruction. All right, as saturation bit, saturation instruction, that once we perform that, it will, for example, we add the number in 8-bit operation, right? So when we add, the maximum number will be 7, right? Positive 7, right? We will never get 8, yeah? So when we add, for example, 5 plus 3, so the result should be 8, right? But when we use the saturation instruction, it will set to the maximum number, which is always 7. So when you add any number that more than 7, the result will be always 7, and this will set this bit to 1 always. Means that it is saturated at maximum number 7, right? So sorry, if 8-bit, right? 8-bit is not 7. 8-bit is 127. Sorry, 4-bit is 7, right? So if 8-bit, so it will saturated at 127 for positive, for negative at 1 minus 1 to 8. Yeah, although you add a bigger number, it will give you the maximum result there. And this bit will be set to 1. We as a programmer will know that by observing this bit. ICT or IT is interrupt continuation instruction, or if then instruction trace bit. So this is mainly for indication that interrupt can be happen during we running a special instruction. For example, multiple load and multiple store. But we not cover in this course. We not using multiple load and multiple store in the course. So we're not going into detail for this one. And this one is some of the microprocessor even don't have this one, right? But this one we have in Cortex M3. Okay. T is thumb bit. We will see later on what is thumb. Empty like this means that reserve, or it is not used. This is the same interrupt continuation instruction bit, or is then, and this is the last 9-bit is exception number. So because exception or interrupt is very big in the microprocessor, so there is a number. For example, the microprocessor is processing interrupt number 0, so all will be 0. in processing number 1, so all will be 1, not all will be 1, the number will be 1, and so on and so forth. All right, so 9 bit, very big actually. All right, so this is condition flags as explained already in detail. So looks at this example a little bit, how the n flag is generated or set to 1. So for example, we add the number in 32-bit for this example. So this is -1, 2, -2. This is -1 in 32-bit. This is -2 in 32-bit, and when we add, we have this value, right? This value. Okay, this is -3 in 32-bit. Ignore 1. Ignore 1 because this is more than 32 already. So we have F, 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 D, which is -3. And look at the sign bit. F means that the MSB is 1. So N is now set to 1. Right? For V flex is overflow. So for example, we add this number together and we get the result like this. Yeah. Like this. So we see here, this is positive number or negative number in 32-bit. Anyone can answer this? A 1, 2, 3, 4, 5, 6, 7 is positive or negative?
Negative, doctor.
Negative, yeah. And the second number will be negative or positive?
Negative also, doctor.
Okay, negative also, yeah. Because the MSB is 1, yeah, both are negative. So you see, when you add this, you have this value, and just ignore this one because this is all carry, right? And this is more than 32-bit already. So you have the result here, 5. 5 in binary is 5. In binary is 0, 1, 0, 1. So you see the MSB now is 0, means positive. If negative plus negative, you should have for a negative result, right? Mathematics. Negative number plus a negative number, you should have negative, right? But your result is positive, means that this is something wrong. All right, and when you check the value here, it is more than 32-bit already. All right, 1, 5, 1, 2, 3, 4, 5, 6, 7 is more than 32-bit. So means that this is overflow already. Just like what you do in 4-bit. For example, you plus 5 plus 3, right? 5 plus 3. Okay, this is positive plus positive. Okay, the answer should be 8. Right? This is easy. But when we look at the operation, if this is 4-bit operation, so 5 is 0, 1, 0, 1, and 3 is 0, 0, 1, 1. And when we add, what we have is 0, we have this 1, and 0, we have this 1, and we have 0, and we have this 1, and we have this. Right? And this is 8. Yes, 8. But in sign number, this is not 8 for 4-bit because this is sign bit and this is negative, right? 1 means negative. And you see positive plus positive value and you have negative value. And this is wrong. Means that overflow, v equal to 1, not fit in 4-bit system. All right, and we know that 8 is actually not fit in 4-bit system because in 4-bit system the number that we can put in is from -8 to +7. 8 is more than +7 already. That's why we have overflow equal to 1. Same as this here. When we have 32-bit, so when we plus, negative plus negative, we should have negative value, negative output, answer, negative result, but we have positive result here, 5 here, positive, right? Means that something wrong already. And when we check using our calculator, this is not 32-bit number already, all right, not fit in 32-bit. That's why we say that v equal to 1. C is easy. For example, we want to add this, yeah, minus 1 plus 1 here, we have 0, and we have this, yeah. This means carry C equal to 1. Z flag is very easy also. Use the same value here. Example here, minus 1 with plus 1, we have 0, although we have here 1, but this is not in the result, yeah, because our result must be 32-bit only. All right, so the 32-bit is 0 0 0 0 0 0 0 0 0. That's why Z equal to 32-bit, all are 0. That's why Z equal to 1 here. All right, so that is the example. Any question? Maybe we continue next week for the memory organization. We will finish our class here, and we will continue the memory organization next week. Okay, thank you very much.